This time, yes, thank you, Laura. Timely focusing on streaming readout, and we just a few weeks ago had streaming readout X, the 10th meeting of that name. And we will have here today from Marco Battaglieri on the latest news from the EIC Streaming Readout Consortium. Markus will give us a summary of the workshop itself, and we will close out with Jeff telling us more about the details on how streaming readout features into the plans for the project Detector 1. Markus, go ahead and start.
Okay, so thank you very much for inviting me and giving me this opportunity to, let's say, repeat the talk I gave to the Streaming Readout 10 workshop. This is about the Streaming Readout Consortium and going through the different, let's say, the history of what we did actually during these years. So let me. Okay, so we presented the proposal to the ERD, the EIC generic R&D activity back in 2018, and the proposal was made with a group of institutions, JLab, MIT, Catholic University, Stony Brook, and INFN. And in particular, Douglas Hazel presented the proposal back in years ago. I don't think I need to, I don't need to go through the difference between a traditional trigger DAQ and the streaming readout. We all know, the difference in terms of let's say the democracy in some sense for the streaming with respect to the traditional one, where every channel is in some way independent and you can or arrange your trigger in the best way. That give immediately this democracy in some sense is giving immediately some advantages in terms of scalability and the simplicity in setting up the trigger. Just why we think is so important. For sure, I mean, future and current experiments are limited by DAQ bandwidth, so this can be a way to go and to in some way to do a better job in that sense. Also, the other things that I think is not always stressed is the fact that streaming readout can reduce the stored data size in a smart way. This doesn't mean that we want to simply measure everything and record everything. You have the advantage or the possibility to reduce your data collected in an intelligent and clever way that is corresponding to a say then of time later on for the offline processing. I think this is a very important aspect that is not always well considered. Also, obviously, we know that we are shifting the tagging, the filtering from the front end to the back end. That means that there is an optimization also on the physics, but also the use of high-level languages. So reuse that, in particular for physicists, I mean, in particular for us, it means that we can do the triggering or have a better control of the experiment. This is also a good way to reuse infrastructure already existing, like a CPU or GPU farms, because since shifting the paradigm from the hardware front end to the software back end, this gives us access to the computing power that is usually already available or easier to assemble and multi-purpose, so can be used for many other things. And obviously, this also goes in pair with the AI and machine learning that nowadays is an important part of this activity. And I think that for the future also we should consider quantum computing that. Obviously, I mean, I barely imagine now to have an AI or ML on FPGAs. I mean, quantum computing seems to be really kind of science fiction. So while using quantum computing to do tracking, for instance, in a single shot, will be probably available in a few years from now. And as I already mentioned, obviously, present some advantage in terms of scale scaling, in terms of upgrade, in terms of adding new detectors. So the configuration is not as frozen as we have usually with the triggered system. And also many experiments in HEP or nuclear physics are using streaming readout. So I mean, I think that there are many advantages. I think that the only big let's say drawback, or what needs to be proved is that streaming readout is as effective as the standard triggering, where we have experience from, let's say, 40 years or 50 years of experiments. So we know, limitation, but we know also performance very well of the triggered system. So this is the main issue that we need to face. From the very beginning, we used this was the kind of presentation we provided to the Streaming Readout Consortium at that time in 2018, and we used as an argument the LHCb proposal for the high luminosity run that dating back, this was the main option for them. Was obvious that they needed to go streaming for the high lumi upgrade of LHC. And then, we on our side, we envisioned that probably, even 4 years ago, that was quite significant, time ago, we thought that for EIC, this could be, an equivalent goal. So going streaming would be, much better at that time. And what we proposed was something, kind of an ambitious program, to develop the entire framework. It was not only considering the front-end electronics or the back-end software or the detector interface, was the entire scheme, because obviously shifting from the front end to the back end automatically requires to have a good software, for instance, that was not really you can in principle with an online and offline analysis you can really decouple the two, while for streaming you really have to have the entire scheme worked out from the very beginning. So this was the original idea. And I already mentioned the main player. Actually, at that time, 2018, the plan was the MIT and was mainly focused on the interface with the ASICs and front-end electronics. JLab was more focused on reusing the flash ADCs at 250 that were widely used in the experiment, or planned to be used in the 12 GeV era. And outside, other institutions like Catholic or INFN, we were, kind of free to develop other alternative solutions, like a digitizer that actually we developed and now seems to be the evolution of the 250. We, in some way, we proposed something that, with an optical link directly connected to the electronics, you don't need to go through the VME backplane, and you have optical links with the powerful FPGA on board that allows you to do a lot of operations that for the flash 250 that JLab had was not the case. And other institutions, like for instance Stony Brook, was more focused on how you deal with data, because data needs to be transferred, needs to be moved and stored on disks. So all that part was in some way split among the different institutions. So we presented a proposal in 2018 in August, and we requested $50,000. And we got $7.5 kilo dollars for the time, $7,500. So it's really, and also, not only we got only a fraction of what we wanted to have, but we also got a very defined and very limited scope, limited to travel mainly, or organizing workshop, not to pay people or to really invest on this technology. Why? Because the committee thought that, this was not yet the time to invest in the streaming readout. So the year after, we requested that we limit ourselves and requested 20,000. That actually we got in the range of 14, again with the very defined scope, travel and workshop organization. And after that, we mainly get no funds for fiscal year 21, and then after 21, mainly the program, the ERD program ended. So, at the end of the day, we got about 22K in 4 years. That is very limited, and also with a very limited scope. Why? Because the DAQ should come after detectors. And so the general idea from the committee was that it was too premature to fund a streaming readout without a detector design. But on the other hand, I mean, we try to convey the message that to design the detector, I mean, for the sub-detectors, it's important to know if, I mean, it is important to know in advance if you are going to have a streaming readout or a traditional triggered readout, because this obviously change the front end, but also change how the different subcomponent can be part of the trigger, obviously. But probably we were not convinced enough, and so to show the advantages and that changing from trigger to a triggerless paradigm means that you also have to think in a different way to your sub-detector. It's our fault, probably we were not able to do it. And then with money provided by ERD23, by the consortium, we were able at least to organize a streaming readout workshop series twice per year, starting from the number 3 to the number 10. Actually, I think that we use a little bit of money left over also for the very last that we organized a couple of weeks ago. And also I think that the main goal, the main success was to be able to create a global community that included not only people interested in EIC, but also to try to have a good guidance from and direction from people that were already convinced that the streaming readout was a good solution, like CERN, FAIR, or DAISY in particular. And I think that, again, as a success of our activity was that we were able to transfer this knowledge to EIC Yellow Report, because if we consider what has been written in the Yellow Report, it's clear that the streaming readout is likely the readout paradigm for the EIC. And the three detectors that follow up, EIC, Core, and Athena, they all, in a way or another, were considering streaming readout as the leading option. So for that, I think that we did right, and that we were able to convince the community. So what was the activity that we did? So first of all, let's say that what we since we were novice in the field, we looked immediately to other experiments that were using streaming readout. On the other hand, we also wanted to keep to understand and keep an eye on the progress in front-end electronics and back-end software in the integration, because these are part of it. And the third main line was about testing the streaming readout prototype at both Brookhaven and JLab, and now in the recent day also at the DAISY with the dedicated experiment, the two-photon exchange experiment, and trying to keep a connection with the EIC detector groups in order to develop the EIC streaming readout framework in a coordinated way. And probably on this last part, as I will show, we probably were not really able to do it. While for the first 3 lines, I think we almost succeed. So let me just go very quickly and very briefly go through these different lines. So streaming readout progress, we started from experimental LHC, CBM, and other experiments that for dark matter or neutrino detection, they were forced to use a streaming readout. And actually, again, we presented the LHCb as a paradigm, but also CBM at FAIR, as that was in particular focused on doing the reconstruction online. That is very interesting also for us, for our experiment at the Electron Collider. Tried us at KM3net, that is an underwater neutrino telescope. You cannot do a triggering while you are 4,000 meters down deep in the water. You need to stream all data out to the an onshore station and then do all your manipulation there. So they were in some way, forced to do it. And also other experiment in like BDX or other experiment at dark matter, where the concept of trigger is not attached or connected to an accelerator, a radio frequency, but is completely free. So you really, you can take advantage of that. So this was the original set of experiments that we look at there. Also on the front end and back end progress, we looked at the AlphaCore, for instance, was one of the company that were providing some work in this direction in developing ASIC that were fully streaming readout compatible. And also, we had the example from Super Phoenix that wanted to reshape the tracking part, the TPC and microvertex part in a streaming mode. And this was, some way useful because this was a living system. And also looking at the network and software aspect, but in particular the software aspect. And I think that another thing that I think was successful was the collaboration and interaction with the software consortium within the EIC development. And this was something new because obviously Trigger and again, the EAQ people were not used to talk with software guys. And we in some way we open up a communication link, and that this was, I think, positive. In terms of testing, what we did was take advantage of Super Phoenix. Again, this was, even if the way they developed at Brookhaven a possible scheme for the streaming readout was an hybrid solution that mixed, a trigger plus a streaming way, but nevertheless there were a lot of problems, a lot of things that we wanted to consider, and we were able to consider, like for instance the distribution of timing, PLL, etc. That is absolutely general for the streaming readout solution. Also, we got some other progress in ASIC, and also the way how you concentrate your data and you stream them out using, for instance, the Felix board that even if it's outdated, I think that anyway, the concept, the idea is still valid. And again, we had the possibility of testing some of these solutions also in smaller scale, like the two-photon exchange experiment at DAISY, that is is a perfect place, or using contribution and using expertise from other institutions that were not the main player, like Brookhaven or Jefferson Lab. At Jefferson Lab in particular, we also developed our own working prototype for the streaming readout. Obviously, we are taking advantage of many experimental holes producing a lot of data. So we have 4 holes running at the same time. With detectors like, for instance, the class 12 that is, or GluX, that are not much different in terms of complexity. Maybe they are similar, obviously, less complex than the EIC detector, but in terms of channels and data rate is not very different from what we are expecting from EIC. So it can be a very good playground. And also, not only for the present, but also for the future, because JLab is expecting to run Muller or Solid to big experiment that will have, again, a comparable data streaming similar to what EIC is planning to do. Obviously, Super Phoenix has the advantage that being a collider, this is the perfect place, because you can really play with solutions that are more matched or similar to what we are expecting to the electron collider. But merging the two, having developing schemes both at the Brookhaven and JLab will provide a complete let's say template for the future. This was the idea. And actually, for the streaming readout at JLab, what we did was to develop the entire framework, as I already mentioned at the beginning. So starting from the detector, we have an entire streaming readout system that is composed by front end, the back end, and online reconstruction, and also the storage and assembling components, and also testing in a more controlled situation, like like a lab, using Cosmics or in a more controlled way, and then moving to a real life, in a real experiment, like in a whole B, we're using class 12 while taking data. This was, kind of the general scheme we had in mind, and actually we assembled the front end using the 250 digitizer. We used the backend developing the TRIDAS, or reusing the TRIDAS that was used for this underwater neutrino telescope, putting together with JANA and the reconstruction, the high level of reconstruction, and then testing, all orchestrated by the CODA, the run control that we are using, adapted to the streaming readout. So it was, a good exercise, reusing pieces that were available, but in a different context and with a different scope. And actually, we do the validation in 2 different configurations. One in using a prototype lead-tungsten calorimeter, just a small prototype made by 9 channels, but reusing the Flash 250 and in Hall D, downstream of the perispectrometer, where you have almost a monochromatic electron beam. We got very nice results, and we were able to compare one-to-one trigger to streaming readout electromagnetic shower development and reconstruction. So this was very nice because it was a controlled situation. And then we moved forward and we used Hall B, where we had the class 12 detector, but in particular a subcomponent that is the forward tagger, made mainly by a calorimeter. Again, a lead-tungsten calorimeter, but in this case it's 300 channels, so it's much more complicated. Also, topology for defining the cluster is much more complicated. And then also we can take advantage of putting together other detector, like an odoscope layer, is the FT Odo made by plastic. So really, trying to do online coincidence by different detectors, just going, a little bit further in complication in terms of this software trigger that we implemented. And actually, we spent a lot of time to do this test and to optimize and try also to understand what we were measuring. And I would say that the results were kind of, nice, because we were able to understand what we measure, even in streaming, showing that if not a fully quantitative understanding, for sure we had a qualitative understanding of the streaming readout. And the prediction we based on a realistic Monte Carlo and giant full simulation of the detector were good enough to provide a 10% level, 20% level of what we really measure. So I say that again, we exercise in a very nice way. So let me say that the list of tasks that we had in mind, even if not funded by ERD 23, were successfully accomplished, let's say. Then suddenly, mainly due to the COVID impact, ERD stops, and we were, in some way, and again, you have to consider that all this activity, in particular also tests, were performed while the COVID was, we were in Medcon 3 situation. The JLab was really tough, really difficult, but I mean, nevertheless, I think we accomplished the program, demonstrating that we were able to develop an entire, streaming readout chain. So, what for the future? So, and what we accomplished in this year. So what the Streaming Readout Consortium was able to do. For sure, I think that ERD 23 was a good starting point to demonstrate with fact that the streaming readout is the solution for the electron collider DAQ. And I can tell you, and I hope that just looking at the size of money that the ERD Consortium injected in the streaming readout, it was not easy to convince that the entire EIC community that the streaming readout was the real solution. But let's say that in particular, the series of the streaming readout workshop was very good to build up a community, and also to let people get used to this change of paradigm. I'm not under-evaluating the idea. I mean, I know that people that are used and expert of sub-detector, they are a little bit reluctant to change a DAQ because they were, comfortable with the standard triggered ones. But I think that, all these discussions were mainly very useful to create this knowledge and this shared knowledge within the IC community that actually converged within the yellow report and the three consortia, HE, Athena, and Core. What we did was keep testing the streaming readout framework, both at Brookhaven and JLab, with the support of other institutions. And this was what we did so far, and what remains to do now is to converge in detector one all what we did. And we have a very strong front-end electronics and DAQ working group that is working on that. And we obviously want to work with them in order to try to convey all the background, all this expertise we collected and we are still working on in the two labs, in order to have a good solution for the future. And obviously, we are also very aware about our limits in our action. So I think that what we learn is that we need a better coordination with the detector working group for the future, in order to share with them solution for the DAQ from the very beginning, and also establish a strong connection with ERD 109 consortium that is more focused on ASIC and electronics. It's not clear if there will be, a future for a generic ERD, or there will be, more focused R&D for the future. This is something that we need to learn, and the entire EIC community is rearranging, reorganizing itself. What we want to do for the future is strengthen the connection and coordination with sub-detector groups. This is something that we have to do, and obviously keep discussing, keep organizing regular meetings that not only involve the EIC community but also get input from external community. That I think is vital, because we need to know, we need to be aware that other experiments are routinely considering streaming readout as a leading option. So I don't see why EIC community shouldn't do the same. Thank you very much for your attention.
Thank you, Marco. Questions for Marco? Anything in the live notes? No, I don't see anything either. Marco, it was very comprehensive and completely clear. Thank you so much. Markus, do you want to take over and share your screen?
All right, let me also unmute. Bear with me shortly. Thank you very much, Kolja, and thank you very much, Marco, for the introduction. I will now give a brief report from our workshop. As Kolja mentioned, was a few weeks ago, May 17th to 19th. As most of you know, Streaming Readout is a workshop series on R&D for streaming readout for the EIC, but also for other nuclear physics experiments. And that was, as Marco has just described, initiated and is organized by the EIC Streaming Readout Consortium, led by Marco and Jan. This whole started in 2017 with an online workshop, and since then we every year met twice for updates. And until the pandemic hit, we were also traveling, and the recent workshops, they have been all online, apart from Streaming Readout 10, where we for the first time tried a hybrid workshop. So we had 74 participants, and about 15 were on site at Jefferson Lab, including not only people from directly the lab, but also we had travelers coming in. Thanks for those for making the effort. This was really nice to be able to meet in person again. For Streaming Readout 10, when we thought about the program, we thought that it would be important to connect where we are in the community. And that is, we had this review of the detector collaboration proposals, Athena, Core, and Action were already mentioned also by Marco. And going from there, we have an EIC reference detector, and we are in process of forming an EIC collaboration to realize the EIC project detector. So we thought it would be good to bring the community together to review the progress which has been done on streaming readout electronics, computing software, discuss future priorities, also for the EIC Streaming Readout Consortium. And we also wanted to have a mini town hall where we really, some people were highlighting progress which they have made in their streaming readout projects. The overall project, or product which we have in mind for the EIC is an integration of data acquisition, analysis, and theory to really optimize our physics reach. So inspired what already experiments are doing in high energy physics, we really would like to have really full integrated commute detector model and have a research model with seamless data processing from the data acquisition to the data analysis. That integrated approach has consequences because it's not necessarily about building the best detector. It is building the best detector that fully supports streaming readout, including fast machine learning for alignment, calibration, and reconstruction, which we would like to do in near real time. And for the goal here is to really have a rapid turnaround of data, which is needed for the physics analysis and which is then the foundation to the EIC publications which we're going out. I can skip the definition what streaming readout is, and I shortly want just to go over the advantages of streaming readout. Marco has also already mentioned them. It is a simplification of the readout, so we have no custom trigger hardware and firmware. The triggerless readout is really ideal for the general purpose detectors of the EIC. We have a broad physics program. We will look at various final states. It is an opportunity to streamline workflow. So you really have in mind a merging of online and offline computing with a combined software stack. And it's really an opportunity to take advantage of other emerging technologies. Marco was already so bold to put quantum computing on the table, but I think we all already see in running experiments AI, which is being used for various aspects of data processing. And at the EIC, we really would like to have the intelligent decisions in all aspects of data processing, from detector, readout, and control to the analysis. And what we also see at nuclear physics experiments, but also already in our colleagues in high energy physics, is heterogeneous computing. This is also reflected in this recent EIC software statement of principles. These are guiding principles to frame the right now ongoing discussion about requirements for EIC software and resulting approaches and solutions. And principle 2 and 3 are related to streaming readouts. So really, we aim for an unprecedented compute detector integration. I already spoke about that in the previous slides. And we will leverage heterogeneous computing where beneficial. Now, coming to the workshop program, we organized the workshop around the points I've just mentioned in the previous slides. We wanted to get an idea of what the status is. And as Marco has already mentioned in the previous talk, the status really depends also on the status of the detector. Then we really wanted to talk, what is our understanding, where we are with streaming DAC. This, of course, requires also an understanding about where we are with electronics and how will we handle data, the messaging of data, etc. And then we looked about what is currently happening in the community. And then at the end, we came back to the community and really had a group discussion about our next priorities. So now let me go through these aspects. Marco already covered the history of the Streaming Readout Consortium, so I leave this part out. And Jeff, after me, will talk about what we know about the EIC detector and the planning of the streaming DAC for the EIC detector. So I also will not cover that, so that leaves me Rolf N's talk on EIC in the era of streaming readout and AI. And Rolf also summarized that we started at around 2018 with really working on streaming. Marco described the full history here, and also Rolf emphasized in his talk about that this is very well connected to what happens in advances in microelectronics and computing and what's happening in other communities. So we really have already made a lot of progress here. Also for AI, and that maybe started in our community to get a little bit more active just 2 years ago, where we had quite some successful workshops, EIC related. And also here we see already first algorithms for the design of the detector, for calibration, for simulations, and for reconstruction. So this vision of EIC in the future, this is already happening now. The community is very actively working on that. And Rolf also emphasized what is happening in terms of heterogeneous computing, really pointing also to our colleagues in Lattice QCD, which are fully taking advantage of combining CPUs and GPUs and modern software, and also pointing on updates from ESNet that we could have maybe in the era of EIC something like 1.6 terabits per second network bandwidth. And of course, a lot of developments in data science to really help us to advance our science. So Rolf really mentioned that this overall product which we have in mind, that this is something which is really reasonable, connects very well, which is happening in the community. And we just have to make it work. It's actually a lot of work and requires a lot of thought. And there was at the workshop a lot of discussion about, well, if we use, for instance, a lot of machine learning AI, what biases do we introduce here? To what extent are these biases similar or different than the biases which we have in existing existing approaches? So that was an important discussion, and we tried to reflect that, write this up a little bit in the workshop report, which we are currently working on. For streaming DAC, I also will not talk about it because Jeff will cover that when he shows a little bit where we are with planning. But what we talked about, quite an inspiration for what we would like to do is what LHCb is already doing and what LHCb is started doing for run 3. So we had Nico Neufeld giving an overview and sharing some experience. And then we had two experts in our field who are really have been working on DAC systems for a long, long time. And this is Dave Abbott and Jefferson Lab and Martin Puschke at Brookhaven, who then were really sharing their experience about what is done. Jefferson Lab at CODA, and Martin presented what is being done at SPhoenix and how this can develop into a system for the EIC. And Jeff, who gave the next talk, he then also showed what has been in the planning from not only the actual protocol collaboration, but then he added the perspective from the SINA protocol collaboration and how this is connected to the computing model. Then we talked about data. We had 4 presentations. The first 2 presentations was really about the messaging. How do we deal with data? We had from Wojciech Slilinski from CERN a presentation on ZeroMQ. This is a really fast and very scalable, extremely scalable messaging library. This is being used not only at CERN, where Wojciech reported, but also we had made some experience on that at Jefferson Lab. And it also inspired a little bit the discussion about what Wojciech was giving to talk about when we talk about streaming readout, to talk about also the slow control components and the messaging to the accelerator, because we need to give some detector feedback to the accelerator. Benedikt Hegner from CERN, he presented PodIO, and that is a very nice way to represent your data model that is built on some lessons learned on how to do data models and maybe not how to do data models in early years from the not only LHC is written on the slides, but also internationally Collider community. And already parts of the EIC community have started to work with PodIO and to use it as data model of the software. We had some discussion about that. PodIO is very well versed for anything which is event level based, but what they have not yet in is modeling for streamed data, where you not have an event build and you just have streams of data and their timing information. But Benedikt discussed that how this is very well possible and how the team could work with the EIC team to make this work. And then we had some lessons learned on how messaging is done. There is, I mentioned before, LHCb is inspiration, but there is also Alice O2 as an inspiration, who do very interesting things. And so we had Giulio Elise from CERN, who was sharing experience from their data model, and really pointing out how important it is at a very early stage to also already simulate the streaming in your full simulation chain and really learn your lessons already there before you then start data taking. And last but not least, we heard from Tom Boccia again, from LHCb Ellen, on what they are doing, also in terms of messaging, but also what is always very inspiring to see is these large GPU farm which they built for their near real-time processing for data. And the Allen team also pointed out that while their focus has been making all these things work for LHCb Run 3, they are already discussing how this could be generalized and maybe used for other experiments, maybe even EIC, and we had some discussions about that at the workshop. Going back from the data and computing to where the data is coming from the readout electronics. Also here we had 4 presentations and a lot of discussion times scheduled. So we had Gabriella Carini from Brookhaven, who shared what is the status and the work which is going on with ASIC and microelectronics. This is Brookhaven has a lot to contribute here, and what work is done to define the ASICs for EIC. Jin, also Brookhaven, he talked about something which is essential to make any streaming deck work, and that is that the timing is well defined and the timing distribution is under control. So this was what Jin in his talk emphasized, and he shared an example how this was successfully done for the S-Phoenix experiment, which will start very soon. And that was also a talk which triggered a lot of important discussion on electronics aspects, on timing aspects for the EIC. Irakli from Sagley, he was talking about front-end organization and specifications. So get the front ends organized, define the protocols, similar to what Jin presented in detail, define the clock distribution, and really think about what type of this infrastructure is common among all of the different detectors. Each of the detectors might have different electronics, but then there needs to be a common infrastructure. And Irakli really went through that in a lot of details, pointing out all the things which we need to define, all the things which we need to understand in terms of protocols, data stream, already mentioned clock distribution, etc. And last but not least, we had Fernando Barbosa from Jefferson Lab, who talked about costing and scheduling. There are already, while in some aspects we talk about quite forward-looking things, there is CD2, CD3 coming in latest by end of next year, and there needs to be certain things defined. We need to have concrete answers on certain questions. And Fernando was talking about the assessment and feasibility of all the front ends, but also getting a really concrete understanding what and verify that what we have in mind in terms of number of readout channels which we have. Then we had this mini town hall, which I mentioned earlier. So I quickly go through there. Joe Osborne from Oak Ridge and Brookhaven, he presented 4D track reconstruction at S-Phoenix. This is already an example. If we have a streaming DAC system, how will we do reconstruction on it? And how do we combine detectors with different properties in the reconstruction? And Joe shared his experience there and his expertise, and this was really also triggered a very interesting discussion. Marco already mentioned AirSub. This is developed by Vadan at Jefferson Lab. And this is really reactive actor microservice based system for streaming readout, really having this Lego brick model in mind, and it is already being tested in Beam in real conditions at Jefferson Lab, and in their various so there's Java, C++ bindings, Python bindings available. Julia is being considered. It works with various DAC technology. So this is a project which is drawing a lot of attention. Related to that, Marco already mentioned that TRIDAS from the astroparticle physics community. So Laura Capelli, she presented the TRIDAS framework and showed that they combine that with AirSub. So the idea is that TRIDAS handles the streaming DAC, and then AirSub does the handling of the data, then more reconstruction aspects. We had there's work going on for machine learning on FPGAs. Sergey from Jefferson Lab was discussing that for a beam test with a GEM-based TRD detector and electromagnetic calorimeter, where they use an FPGA, and he was presenting the work which is happening to really, for instance, do particle identification on an FPGA, and all the work which has been done and what is planned in this quite interesting project. Ronglong Fang from ODU, this data scientist, he presented algorithms for automated change detection, which then really allows automated data quality monitoring, and is important to define new periods where calibrations should happening. And he showed this also based on real data coming from a GEM detector, just one detector prototype, and also data from the SPS experiment, which just started in the last run at Jefferson Lab, and will continue in the upcoming run. And last but not least, we had also Tori Eske from Jefferson Lab, who presented machine learning for calibration and control of, and the example was a drift chamber. So it was really to have a system which can react to changes in, for instance, atmospheric pressure or in the gas temperature. And you see here on the right really how well the system works. And they have done a really successful tests in making a machine learning based responsive system work. They first did this on a drift chamber, and now they also would like to look at other detectors at the GlueX experiment to gain more experience. Last but not least, and also, sorry, running out of time, is the streaming readout community. So at the end of the workshop, we came together and made a list of priorities. I will not read them all. We will have them in a more structured way in our workshop report. But what we discussed are a coordinated effort on streaming readout. We really discussed what is the timeline and the design for the development of a streaming readout system for the EIC. There are questions, and we had many in the audience who really were pointing out the urgency on many of these questions. So you see a long list here. And then we have some more detailed questions. I already spoke about the understanding the biases in the system. How do we do data quality monitoring for each layer of the readout? If we go for such a system with near real-time processing, what computing resources are needed? How do we manage background and noise? We need to understand when we talk about we want to do autonomous calibrations. We first need to understand how would we anyway calibrate and align the EIC detector. This is highly non-trivial. The EIC detector is almost 100 meters long. So alignment and timing everything in, etc., and calibrating everything could be quite a challenge. To what extent would we like to take advantage of FPGAs? Now with all the troubles with the supply chains, but even if we would not have these troubles, how do we coordinate the purchase of electronics, which we need, of other components do we need? I already spoke about the importance of the clock distributions. And Marco already also mentioned something very important in his summary, is that this EIC Streaming Readout Consortium really helped in bringing people together so that the DAC experts are talking with the computing experts, are talking with the software experts. And we really do not want to have this isolated efforts. We see this as a whole effort where we are all talking and trying to define the best system for the commute detector integration at the EIC. But there's a discussion how to define what are the boundaries between the various systems and what is our common understanding about the full integration which we are aiming for. So let me conclude here. We had a workshop on streaming readout R&D for the EIC. All the discussion is informed by other nuclear physics experiments, and not only nuclear physics experiments, but it's also relevant for other upcoming nuclear physics experiments, for instance, at Jefferson Lab, Solid and Möller. We have started with a workshop report, and we will share when we have a full first draft. We are right now maybe at 50%. We will share that with all the participants for comments, and then we make this as a resource available. It was also at the end of the workshop said that this is really helpful, these discussions. We definitely would like to continue the series, and we really saw the need to have a next one by the end of the year. People were talking about November and or December. Thank you very much for your attention. That was all from my brief summary.
Thank you, Markus. Dense summary of a dense and productive workshop. Questions for Markus? Let me ask, who will be the host, and do you think it's going to be hybrid, or will we finally have a full in-person thing?
The host has not yet been decided. That's something for the Streaming Readout Consortium to decide. After 2 years of the pandemic, I gave up making any predictions about will it be hybrid or not.
That's fair.
I can only tell you that it was very, very nice to have it in person and to really have visitors at the lab. So really, really great. But we also needed to learn a little bit how to do these hybrid workshops well, because we got so used now that everyone is on its own Zoom screen. And now suddenly we're in a meeting room again, and we were to the old troubles, or people could not hear, and someone in the audience was asking a question. So there we need a better job. So we've realized, for instance, at Jefferson Lab, that we really need meeting rooms where we have good microphones in there, so that this really works, that people can discuss, and the people who are connected via Zoom can follow the discussions very, very well.
Yeah. No more questions? And thank you, Mark. Yes, go ahead.
I was just saying thank you.
Thank you. Jeff, are you with us?
I am.
Yeah, I see you. You want to share your screen?
Yes, I do.
Thank you very much.
Okay, thank you for inviting me to give this update on the streaming readout plans for detector 1. I'm always feel funny saying detector 1. I don't think it has another name yet, though. I'm presenting this for the DAC working group, and the conveners of that group are Alexandra, Chris, myself, and Joe Schambach. So first of all, I want to talk a little bit about the detector. Coming out of the DPAP process, the HA detector was selected as the baseline. But of course, there's the expectation that that basically these collaborations would merge. So the 1.5 Tesla magnet is one of the things that I think is pretty sacrosanct, that won't be changing. But many aspects of the design are being further refined from the HA detector with the addition of a lot of additional expertise. I always have trouble counting detectors. There are 20 bullet points here for the HA central detector. But of course, many of these are effectively the same detector. All these various ITS3 mapped silicon disks really are the same detector, but roughly 20 different detectors in the central region and another 10 in the far forward and far backward regions. And unlike some detectors, like the detector I work on in STAR, there's no one detector that is really the central most important detector. All of these detectors have kind of mutually important, they all are required for each of the other ones to work. There are sort of 5 main classes of technologies, and you have to have pretty blurry eyes to agree with this, but silicon maps, MPGDs, gas detectors, the AC-LGAD for like the TOF and parts of the far forward detectors, rich detectors. In HA, there's 3 proposed rich detectors, and calorimeters, which mostly will have SciPM readouts. I want to move right on to kind of the expected data rates. So we should always keep in mind that the beam crossing rate is 100 megahertz at the EIC, and the maximum event rates are expected to be around 500 kilohertz. Many of the beam species will have rates far less than that. I want to kind of show this slide. This was produced for Athena, but it's simulated data rates. You see the data rates for the collisions, but also for the proton beam gas and the electron beam gas. And as long as you want to talk about orders of magnitude, I think this is equally valid for HA. And the points here, if you look at this final column, this is a simulated output of hits. And the data volume is quite small. This is about 13 gigabits per second. This is the DAC output. So it's the same number, but it's based on estimates from the detector experts. And it's significantly higher. I believe this probably includes some noise. Maybe it involves some conservatism. And then this next column over here, going in reverse order again, is the input to the DAC. That is the input to the DAC computing. And this number is much higher. And this is dominated in Athena by the D-rich and the PF-rich, which are rich detectors that use SciPMs as their readout. But these SciPMs have to be sensitive to single photon events. And for that reason, they have to have a very low threshold, and they're sensitive to dark currents that are dependent on the irradiation of the IPMs. So notice that these numbers, even this number for the output, are dominated by noise, right? It really doesn't matter if we're running at 500 kilohertz or if we're running at 0 kilohertz. We're still going to get close to this kind of rate into the detector at the front end. In terms of the scale of the actual system, I do show both ECHE and Athena because the counting is a little inconsistent. I just want to say that reconciliation is in progress, but roughly speaking, we're talking about 4,500 fibers, and we're talking about on the order of 2.5 million channels. This might be as high as 10 million in ECHE. But I broke out channels for kind of conventional detectors versus maps, and I broke out these as 57K maps sensors. The reason for that is that each of these map sensors has something like 1 million potential pixels. So it gets a very hard to compare numbers. And these will be read out into somewhere between 120 and 140 Felix boards, or as they're called in ECHE, data aggregation modules. So the idea here is that we're going to have a huge number of channels, but relative to CERN, very small total data throughput, at least for the output data from the DAC. The numbers of fibers are set mainly by the detector topology and the electronics requirements, not so much by the data throughput. If you look at the total numbers, you're talking about the 4.5K fibers, and even using the biggest data volume estimate that we had on the previous page, this would be about 1 gigabit per second per fiber, which is less than 20% of what the fibers can take. But noise reduction is going to be the key. And as an illustration of that, just imagine one hit per bunch crossing. That would give us about 5% of our full output data bandwidth. So we have to really do a good job of reducing the noise. So everybody has seen streaming data acquisitions, and this is from the ECHE proposal, I believe. And the streaming idea, it was part of the yellow report reference detector and also the readout for all 3 proposals. It's typified by no external trigger. All the collision data is digitized, but aggressively zero suppressed at the front end electronics. The event selection, so basically our expectation is that in normal running, we'll have 0 dead time. But of course, it's hard to say that that will be true all the time, because if there are issues with overutilization of links for whatever reasons, we may have to impose dead times in order to get consistent data out of the system. But we hope to keep those low. Event selection can be based on the full data from all of the detectors in real time or later on in reconstruction. A lot of times I've been hearing that there is no trigger bias in a streaming DAC system, and I don't think that's true. Remember that you still have to do event selection, and it still has to be based on your actual detector data. The advantage that you have is really being able to investigate all of the different detectors because you're doing it at a later stage and you don't have as strict time constraints. But of course, there still will be whatever biases your detector imposes based on acceptance and other detector facts. The data flow, however, is one direction, and it's mostly independent, certainly through the point where you get into the commercial off-the-shelf computing, which starts at this the event buffers and data compressors mode here. So you have the fees and the DAMs, the DAM boards, are the envisioned as Felix boards currently. And these are the boards that accept the fibers and connect to the PCs via PCI X bus. So all of the data from the EBDCs through the buffer boxes are in a commercial off-the-shelf computing connected by Ethernet switches or by Ethernet network. So this one direction data flow into the DAC computing means that there's really no global latency requirements. Avoiding a hardware trigger also avoids the complex custom hardware and firmware. And one thing to note is that the front-end processing, which in the yellow report are the programmable hardware that lives between the FEEs and the DAC computers, in both of the proposals was de-emphasized relative to the yellow report, but it definitely should not be precluded. This might help us by, for detectors that have very low data volumes, by aggregating the data without doing much analysis. It might also be an opportunity for things like artificial intelligence or machine learning data reduction. And of course, the data volume has to be reduced as much as possible at each stage. So I want to give a summary of those proposed data reduction techniques. They include timing windows with respect to the collision time, which would be done in the FEEs, zero suppression also in the FEEs, elimination of hits that aren't part of tracks, either via machine learning tracking in the front end processing or at any point later with any kind of tracking algorithms. You can also eliminate hits that are not part of Cherenkov rings. This is very similar in flavor to the previous item. Feature extraction. This might be reading out the centroid instead of the time, and cluster finding, which is an example of feature extraction in my mind. There's also a software trigger that's possible to be implemented either in the Felix boards or in the initial stages of the computing. And finally, there's proposals for lossless compression in order to reduce the data volumes. Additionally, I think we should also be investigating features to improve these above techniques. These might include things like automated thresholds, pedestal values that are computed on the fly, common mode noise suppression, things like this. We also want to maybe do dynamic control of the calibrations and slow controls and or of the FEEs, right? I guess this is similar to the previous element. Dynamic monitoring and removal of aberrant channels and automated recovery of things like single bit upsets. Returning to the system architecture. So despite the kind of conceptual simplicity of the data flow, just moving from the detector straight to the offline computing, the full data flow isn't really that simple. The timing system, as was mentioned in both the previous talks, is quite critical. It has three major functions. One is to synchronize the detector data, just to make sure we're looking at the same data from different detectors, same collisions. And that requires a synchronization on the order of 10 nanoseconds. Some detectors, however, have much higher time resolution needs to be synchronized. This includes, for example, the TOF. And also importantly for the DAC system is that the timing system is the only source of real-time information that's shared by all of the detectors. So any kind of coherent calibration events or potentially busy feedback, raw readout requirements, things like this have to come through the timing system. So there's two parts of the timing system in my mind. And the first part is this interface between the collider, the run control systems, and the Felix boards. And it provides a clock to the Felix boards, but it also provides information to the entire DAC system. And Martin Perschka presented S-Phoenix's timing system, which does all of these things. It's a method for communicating this kind of information. One feature of it is that it communicates, I think, 40 bits to the Felix boards, but only 20 bits of that has to be transmitted up to the FEEs because the FEEs only have to handle a limited amount of time worth of data at a time. The second part of the timing system is on the FEEs, and it provides the interface between the electrical components and the fiber itself. I think there's a consensus that the recovered clock is probably good enough for most detectors, but some detectors, such as the TOF, might need a dedicated clock fiber. This needs to be resolved. But a point here is that this interface is just one aspect of the electrical optical interface to the data acquisition system. And this is part of the FEEs, but the optical part has to be the same for every detector, while the electrical part is going to be different for every technology. So, we recognize the need for a collaboration-wide coordination of this, but the form and content of that is currently under discussion. I do want to explain. Yes, question? Okay, so I wanted to mention why why this is so critical. The interface, of course, is shared among all detectors. It needs to be reflected in the fee requirements, so it has to be specified early. It needs to satisfy all the requirements of the detectors, all the running modes, and it has to be replicated in every fee, so cost is certainly an issue. And finally, it will really define the capabilities and the limitations of the DAC system, and this is next to impossible to change or replace once multiple detectors have been implemented. There's also thorny issues here. Radiation might be an issue in certain areas, at least. For example, synchrotron radiation. Congestion is one of the big risks in a streaming DAC, and it's difficult to monitor and control a congestion with a congested link. So we have to think hard about how we prevent that from ever happening. Also, most of the detectors are planning on using CERN ASICs or modified CERN ASICs, and that might force us to support a 40 megahertz clock, which is particularly inconvenient given our 100 megahertz bunch crossing rate. So this is a big item that has to be resolved. Do we need to support 40 megahertz? And if we do, how are we going to do it? There's a lot of options that are under discussion. LPGPT, which is kind of a set of chips that helps do exactly these items. But we also have the possibility of bare FPGA-based systems with commercial fiber electronics. There's the JLab timing system and the SPhoenix system. And another idea is that we might need multiple solutions for different detector technologies. So we need a detailed understanding from the detectors of their needs. And we also need kind of a quantitative delimitation of these options so that we can resolve these issues. We are taking actions towards resolving them. I think this is a good candidate for a sort of topical meeting of the streaming workshop, just entirely on this part of the interface. But we also are trying to coordinate with the project electronics and DAC cams. We're giving it a lot of attention in the DAC working group. And we're also defining, detector group contacts with expertise to try to foster these dialogues. Note that the people that are in parentheses here haven't committed to doing anything. I've included them because of their past willingness to share their expertise, not because they've committed to giving us any information whatsoever. Returning again to the system architecture, we've talked about the timing system. I also want to talk about the configuration system because this is also potentially quite complex. All of the ASICs and stuff require complex configuration, but we also want real-time control for providing features like, perhaps raw data to check the bias due to this aggressive compression. And the only place, again, we have to do this through the configuration or possibly through the timing system. We also need to be able to adjust the configuration in real time in case pedestals drift or hot channels come up, or in order to track failing electronics. Slow controls integration can also be important for the same reasons. One of the talks at this streaming workshop was about adjusting high voltage settings using AI and ML control. And my point is that this should not scare us. It might not be that interesting from the point of view of AI or ML research, but it would be really useful for us. I think of this more in terms of having a thermostat for setting the high voltage to control something like the gains of a detector. It's easy to monitor that it's working right, but it's extremely useful if you have a detector that has gains that are shifting. Also, of course, you need things like automated power cycling and recovery. I want to give just a couple things. If you kind of step back, the entire DAC system we've been discussing is sort of over here in this corner. We're going to step back and look at the entire computer module or model architecture. And the streaming readout idea is an opportunity to rethink DAC as just one component of this full computing chain, all optimized, as Markus mentioned, for the production of physics data and as close to real time as we possibly can. These are slides that were presented by David Lawrence that kind of illustrate this. The idea here is that this data, although it takes more than, this offline buffer for doing calibrations takes several weeks, it's still very quick. And the data that's actually reconstructed never goes through the raw storage. All of the collision data is stored but it's stored for archival purposes, not as part of the reconstruction needs. And of course, the final processing is going to be highly distributed in kind of this EIC butterfly model. So as you blur these responsibilities, I do think we have to consider what I consider to be kind of core DAC or even trigger capabilities when you're discussing these blurring of the computing. These things include things like scalars and online QA, monitoring the detector performance with metrics like uptime, monitoring the beam for collider feedback, and keeping track of the events and event types to track physics goals, as well as goals for the collider and operations groups. So these involve very short timescales. You have to be able to report back to the collider that day if there's some problem with the beam. So if this is done in an offline context farther up than within the DAC system proper, then the sociology of those groups has to change to pay attention at very short timescales. Finally, the summary is, I've presented the plans for the streaming readout for our detector and highlighted some of the current areas of attention. And obviously there's a lot of work yet to be done. So join us if you're interested. Thank you.
Thanks, Jeff. You have many files on your desktop.
Yes, I do.
Questions for Jeff? Okay, then we have time for a more general discussion. Any questions for any of our panelists? Comments, thoughts? Very good. Then we can give you back 10 minutes of your life. And just announce the next workshop, the next roundtable, which will be the third in our series on analysis techniques and tools. And we will have probably, we know we have somebody from Root. We have a summary of analysis ecosystems too. And we're working on highly parallel amplitude analysis with AMP tools. And I hope to see you then on July 12th. Thank you so much for joining. Bye.
Bye-bye. Thank you.